Hello everyone, this is the first lecture, the Intro to Computer Graphics, Principles of Graphic Systems. I'm Dominic Mendel, and I'll be followed by Jessica and Neil. Here's our contributions that we worked on for this project and presentation. We'll talk about these as we go on. So the first thing I'm going to be talking about today is CRTs, which are cathode ray tubes. Essentially these are old television sets or monitors. We don't use these nowadays anymore in 2019, but we're going to talk about how they work. So they work by using this cathode ray tube, which essentially shoots an electron down the path onto the screen. So that's why these TVs were so big, was they would shoot electrons to the front of the screen. So the front of the screen has a phosphor coat on it, and that is what becomes charged and emits light for the television. Right now I'm only going to be talking about the black and white televisions, and I'll get into how they use color. So something to note is the phosphor, when it gets emitted by the electron gun, can lose the amount of energy which shows you the light that it's emitting. This is going to be known as the refresh rate, which is the frequency at which the picture is redrawn, is the refresh rate. So what that means is the electron gun has to keep shooting these electrons in a specific point to re-emit the phosphor, so you can see the screen, because these refresh rates for the phosphors that they used could range from 1 millisecond all the way up to about 1 or 2 total seconds. So the electron would have to hit each point of the screen, and then within that grace period of between milliseconds to 1 or 2 seconds, it would have to go back and re-hit the phosphor, because if you didn't, you would see the video quality start to drop. So there's two major components. One of the major components is the filament. So at the start of the ray tube, you have your connector pins, and then you have a cathode which has a coiled wire in it, which essentially shoots off the electron. They do that by turning on the connector pins, electricity flows through it, it gets heated up, and then the electron shoots out. So that's essentially what's going to be firing off the electrons in the tube. So to control that, they use these deflection plates, as you can see here. So there's the horizontal deflection plates, and then there's the vertical deflection plates. The horizontal deflection plates will control the vertical motion of the electron beam, and the vertical deflection plates will control the horizontal motion of the electron beam. As I mentioned earlier, the persistence of the phosphors on the screen is how long the light will emit from the phosphor-coated screen. So now I'm going to be talking about resolution. So we all know resolution nowadays can go anywhere from like 1080p to we got like 4K and whatnot. So we know this term called pixels. And back when we used CRT, the phosphors would emit too much light. So if you take this figure 4 here, this would be the point at where the phosphors hit with the electron beam, and the points to the left and the right would still be emitting light, but not as much as the main focal point. So the issue with that is you can't hit too many parts of the screen without there being a blur of light. So figure 5 shows that the percentage that they used was about 60% before they spaced it to the next pixel. And then the row and column arrangement of these pixels is what we call as resolution. So you can see here that the cathode ray tube would hit right here, and then the next spot would hit right here. So there wouldn't be too much overlap of light, and it would require less, hitting of the electrons, while also looking as a clear image. So now I'm going to be talking about a random scan display, which is a type of CRT. It wasn't used too commercially. It was mostly used for like engineering purposes when you wanted to see fine lines. So a random scan display essentially drew perfect lines on a screen. As you can see here on the random scan display, you have your nice Pikachu, which is perfectly lined. Whereas a raster scan, which Jessica will talk about in a couple slides, is a little bit more blurry. The difference is that random scan displays can't have shadow effects, whereas raster scans can. So raster scans were more desirable for like television and stuff, but random scans were for engineering purposes or medical purposes where you needed to see fine lines, but they weren't commercially used as much. So now I'm going to be talking about the color CRT monitors. So there's two proposed methods. The first method is layering the screen with different phosphors. So you would have the front of your screen here, and then instead of just one coat of phosphor, it would have multiple coats of phosphors. And then the electron gun would have to penetrate some number of those layers to emit different light. So for instance, if you wanted to see red, you might only have to emit to the first layer, but if you wanted to see something like blue, you might have to penetrate all three layers. And then the controlling would have to be done through the single electron gun, and then the layers of phosphors made things a little bit too complicated and too expensive. So the second proposed method would be the shadow mask method, where instead of using one electron gun, you would use 3 electron guns. And the 3 electron guns would have different powers, and they would also be different colors. And they would use the 3 colors that we know as red, green, and blue, or RGB. These RGB electron guns would be shot at the single phosphor screen in a triangular manner, and the voltages would vary depending on the color pixel that you would want. Because as we know, RGB is our 3 primary colors, which depending on the ratio of RGB, we can get upwards to about 17 million color choices per pixel. It's worth noting that the color CRTs still behave in the same manner. They would shoot a single point. It wouldn't be like the blue shot in a corner and then the red shot in the other corner. They would always shoot in the same position. So now I'm going to start talking about flat panel displays, which are not CRTs. CRTs are the big box TVs that, are a little beyond our time. So the flat panel displays, there's 2 types. There's emissive displays and non-emissive displays. Emissive displays convert electrical energy into light, and 2 good examples are the plasma panels and LEDs, which I'll go into more detail about. And non-emissive displays convert optical effects to convert sunlight or light from another source into graphical patterns, such as LCDs, which are a little bit more complicated, but I'll explain that. So I'm going to be talking about plasmas, which is going to be these left diagram for now. So the way plasma panels works is it has 2 glass plates on the left and the right side, and in between the glass plates you have a gas, which is usually some sort of highly excitable gas, such as neon, which would emit color. So conductors would be stripped along these glass plates, and the conductors would be turned on, the gas would be heated up, and it would turn into a plasma state, emitting off some sort of light. So you would see that light through the monitor, for instance, and this would happen at every pixel. And the color variations would be based on such as like how long is the exposure for the neon, how high is the temperature. Those kind of factors would change the color that neon burns. It would fire off voltages at each pixel about 60 times per second, so it's always continuously burning off neon and reusing the same neon. So now I'm going to talk about thin film electroluminescent displays, which is a very similar concept, except instead of using a gas like neon, it's actually going to be using a solid phosphor, which usually it was zinc sulfide doped with manganese. So it was not a gas, it was a solid, but it's the exact same setup. You have your glass plate on 2 sides, you have your conductors, and then it would heat up the center. So before it heated up the gas, now it's heating up the solid. And it would behave the same, but it wouldn't turn into a plasma state. It would just emit some sort of light in the exact same manner. So we're just going from a solid from a gas. So hopefully you can see this on your screen. I tried to make it as big as possible. So we're going to talk about now LEDs, which are hopefully everyone should know by now is light emitting diodes. And this is usually what modern day screens are going to be made of. So each pixel is going to have 3 LEDs, one red, one green, one blue. So if you see in this little corner here, hopefully, you should see the blue, the green, and then the red going from left to right. So these 3 diodes are going to be turned on and off uh, from a percentage from 0 to 100%, giving you your 17 million colors. So for each pixel, you should have 3 LEDs. And these LEDs will show you the screen that you want. So LEDs are very efficient. The only issue with LEDs is showing a true black, because other LEDs will shine brighter than the LEDs that are turned off. So you might notice when you turn off your screen or show a black image with your monitor on, you'll have a backlit of sorts. Lastly, I'm going to be talking about LCDs. So LCD stands for liquid crystal displays, and they're probably the most complicated. So the name comes from this part here. So what we have is a glass screen, which is what the user would be looking at. The user would be looking through here per pixel. And you would have this crystal structure at the top here. And you would have these 2 conductors on the sides that are polarized. Current would flow through this, and it would convert this crystal into a now liquid state. So we're going from a crystalline state, or a solid, into a liquid crystal state. And by this effect and the polarized film that's here, it'll change the color that you see through the glass. So the name comes from the crystal becoming a liquid, and then once you turn off the conductors, it goes back to being a crystal. So it's continuously being turned on and off, and by how much you want it to be liquid could change the colors that you would get. I believe that if it's completely liquid and all of the light passes through, you would get a very bright effect. If you dimmed it down and some of the crystal stopped the lighting effect, you would start to get colors.
So now I'm going to talk about display devices specifically with stereo imaging. So stereoscopic views is another technique to represent a 3D object. However, with stereoscopic views, you actually do not produce a true 3D image. And what happens is that stereoscopic views actually create a 3D effects by presenting a different view to the left and right eyes. So usually 2 views of the same scene will be generated along the viewing direction and position of each eye to the scene. So there will be an image taken from the position of the position and viewing direction of the left eye, and then another image of the same scene will be taken from the position and viewing location of the right eye. These 2 view images would then basically end up merging into a single image, and this would create a scene with depth. So as you can see over here, this would be the left eye image that would be taken of this car, and then this would be the right eye image that is taken. And then when it's projected in front of the user, the left eye image projected in front of the left eye, and the right eye image will be projected in front of the right eye. And these 2 images will end up basically kind of like merging together to create one image that will cause a 3D effect. So then moving on. So let's talk about the stereoscopic effect on a raster system. So one way to produce it is to display each view on alternate refresh cycle. So as mentioned before, as Dom mentioned before, that to keep an image on a display, you have to keep going through a refresh cycle and keep basically shooting those electron beam out to create those pixels to keep that image going. So one way to produce the stereoscopic effects on a raster system is to basically display each view on alternate refresh cycle. So you will display the view of the left eye image and then the view of the right eye image on the next refresh cycle. So usually this screen is viewed through glasses, and the lens of these glasses act as a shutter that basically rapidly alternate to block out one of the view each time. So it will either block out the left view or right view rapidly, and basically this causes the image to blend together and create that 3D effect. And the glass over here is an image of a glass that would be used for a stereoscopic scene in 3D. So looking at these two images right here, these two images are of the exact same scene. However, if you look closely at them, they are not exactly the same image. This image over here, this is actually taken from the perspective and viewpoint of the left eye. And then this image over here is taken from the perspective and viewpoint of the right eye. So even though they are very similar, if you look closely enough, they are very slightly different. And these are basically an example of images that will be taken for stereoscopic viewing. So when these two images are placed in front of the eye, the left image on the left eye and the right image at the right eye, at the way that you look at it, it will end up merging into one image and create a 3D effect. Alright, so now moving on to talking about virtual reality devices as part of display devices. So to begin with, I don't know how many of you actually have experienced virtual reality before or know much about virtual reality, but virtual reality is basically the concept that there's a virtual environment that a user will feel like they have stepped into and can interact with. So that's what virtual reality is. It's just a virtual environment that a user feel like they are now a part of and can interact with everything. So virtual reality devices actually use basically stereoscopic projection to create this virtual environment, this virtual reality feeling. So there's actually 3 ways that you could create this basically virtual reality environment. And the first way is through a headset containing an optical system to generate the stereoscopic views. And then the user will have interactive input device to be able to interact with objects in the scene. The second way to basically create this stereoscopic projection in virtual reality device is by having a bunch of projector generate a scene along an arrangement of wall. So then the user will wear a stereoscopic glass, and they will have data glove to be able to interact with the virtual display on the wall. And then the third way that you could use stereoscope projection with virtual reality device is having graphic monitor. So this is the most basic and I guess cheapest way that you could produce this virtual reality environment. You have graphic monitor. The user will wear a stereoscopic glass again, and then there will be a head tracking device. And the head tracking device will basically track the movement of the head and change the scene view that the user will be seeing depending on the movement of the head of the user. And these head tracking devices will usually be placed on top of the graphic monitor. And with the third way, there's really no interaction with the virtual environment. It's just more of the seeing the virtual environment. Alright, so now let's talk about raster scan display for display devices. So as Don mentioned before about raster scan display and the difference between random scan display, he talked more in depth about random scan display, so now I will talk a little bit more in depth with the raster scan display. So the raster scan display is actually the most common type of graphic monitor that employs a CRT. So what the raster scan display does is that it displays an object as a set of discrete points across the different scan line. So if you look over here at this image, A, B, C, D, every single line that is shown here, those are all scan lines. And as you can see here, is that there will be an electron beam that will basically whip across the screen from one row at a time, from top to bottom, and it will go from basically left to right, top to bottom, and it would just like goes like this over every single line. And when it goes over every single line like that, it will create a pixel at a certain location on the scan line where the pixel is supposed to be. So the beam intensity is altered while it's moving across the scan line to create basically different pattern of illuminated spots of different color. And usually the picture definition that needs to be displayed is stored in a memory area called the refresh buffer, which is also known as the frame buffer or the color buffer. And in this buffer, the set of color values for the screen points are stored and then are used to control the intensity of the electron beam. And these buffer could also store other kind of pixel information too, beside colors. So that's why altogether, all these buffer will be called a frame buffer. So the type of phosphor that's used in the CRT and the number of bits per pixel available in the frame buffer actually determine the range of colors and shade of gray that can be displayed on the monitor for raster scan display. So for black and white images, you only 1 bit per pixel. And these frame buffer that has 1 bit per pixel are called bitmap. And these bitmap are basically just patterns of binary values. So as you can see over here, this is an example of what a bitmap will look like. It's just a black and white images, and the way that it functions is that since black and white images, for the beam intensity, it would just be either a 0 or 1, depending on whether it's black or white. So that's why you only need 1 bit. It's just be 0 or 1. And then with multiple bits per pixel, that's what is needed for color images. So if you want color images, you have to have multiple bits per pixel, and frame buffer that contains multiple bits per pixel are called pixmap. And this total image over here is an example of a pixmap. So a pixmap is basically a multicolor pattern. And with this, to be able to get these different color, you need multiple bits per pixel, because instead of just 0 and 1 to get black or white, you need a range of number between there to be able to get a different color and a different shade of gray. So then the number could actually be like 0.5 or 0.7 or something like that, depending on what the color you want to make it. So now let's talk about the refresh rates of raster scan display. So as Dom has talked about before with refreshing, and I have talked about before refreshing too, we know that refreshing is very important when it comes to displaying images on these screens or monitor, because to maintain the image, you have to keep refreshing it every single second or so, because you need to keep shooting out the electron to keep these pixels basically illuminated, these spots illuminated on the display. So with raster scan display, the refresh rate is usually 60 to 80 frames per second, but it could go up to 120 frames per second. However, some raster scan display do have a variable refresh rate depending on the application of the raster scan display, if it's for a specific type of use or something that needs the variable refresh rate. And then also refresh rate can be described in units of cycle per second. So basically in hertz. So if you have 60 frames per second, that will basically equal to 60 hertz. Now let's talk a little bit about horizontal retrace and vertical retrace. These are actually very important when it comes to raster scan display. So the idea of the horizontal retrace is that the electron beam will return to the left side of the screen at the end of each scan line to begin displaying the next scan line. So as I've mentioned earlier, the electron beam basically goes through each scan line from top to bottom, from left to right. So once it reaches the end of the scan line, horizontal retrace is the process of where the electron beam will go back to the beginning, which is to the very left side of the next scan line, so that it could go through that next scan line. So that's what the horizontal retrace is. With vertical retrace, the idea is that the electron beam will return to the upper left corner of the screen at the end of each frame to begin the next frame. So the vertical retrace only happens once the electron beam has gone through every single scan line in that frame. Once it has finished that, it will go back to the upper left corner to basically start going through all the scan line again for the next frame. And now let's talk a little bit about interlacing this procedure when it comes to raster scan display. So basically, interlacing is a procedure and a way to display scenes better when the refresh rate is really slow. So by using interlacing, it will help to avoid flickering of images when the refresh rate are slow. The only downside with interlacing is that it only works well when the adjacent scan line have very similar display info. So if they have very similar colors, then it works well. But if they have very different color or very different display info, then it doesn't work really well. So what happened with interlacing is that basically each frame that is going to be displayed occurs in 2 passes instead of 1. So on the first pass, the electron beam will sweep across every other scan line from top to bottom. And then after it's done with its first pass, on the second pass, the beam will sweep out the rest of each scan line after the vertical retrace. So as mentioned before, the vertical retrace is when it has gone through the whole entire frame and gone back to the upper left corner to start again. So that's just what happened on the second pass. When it goes back up to the upper left corner, it goes through every other scan line that it didn't do in the first pass. So for example, if on the first pass it goes through all the even number scan line, then on the second pass it will go through all the odd number scan line. And what happened when it does this is that it ends up displaying the entire screen in half the time it would take for the beam to sweep across every single lines in one pass. And as we know that our eye is not perfect and there's a lot of flaw with our eye. So because of how small these electron beams are and how close they are to each other, and if the color values are the same and the display image is the same, if it goes through and does every other scan line, our eye would basically blend all these pixel points together to create an image, even if it doesn't have every other line displayed yet. So that's how interlacing works. Now that we have finished talking about the raster scan display, let's actually talk about the actual raster scan system. So the architecture of the raster scan system is that it's usually composed of several processing units, and of course it has the main one, which is the central processing unit, which is used to compute any kind of calculation or any main processing that it would need. And then it also usually have a special purpose processor beside the CPU. This special purpose processor is either called the display controller or video controller. The raster scan system usually also have a system memory that will contain the frame buffer, and then the video controller will usually access the frame buffer to refresh the screen. So looking at these images here, so this top image up here, this is a image of the basic architecture of what a raster scan system will look like, just a basic one. So here we have basically a system memory, and in the system memory, the frame buffer exists in here somewhere. And what happens is that the video controller will basically access the system bus to access the system memory to be able to access that frame buffer, grab values from that frame buffer to basically produce the refresh for the monitor. And then this image down here, the second image right here, this one is also a sample architecture of a raster scan system. However, this bottom one is a little bit more complex than the top one. And the fact that right here, the system memory, inside the system memory, there's actually a dedicated area for the frame buffer. So the frame buffer is actually has a specific area for itself inside the system memory instead of it being just somewhere random in system memory. And then with this design, the video controller actually have direct access to the frame buffer to be able to grab information from the frame buffer to do the refresh for the screen. Alright, and so now let's talk about how the raster scan system actually function to be able to basically grab these value and put out the pixel and do the refresh and stuff like that. So this image over here right here is basically a simplified structure of how it will work. So there are usually two registers that are used to store the coordinate value for the screen pixel, an X register and a Y register. The content of the frame buffer at the current pixel location will be retrieved to set the intensity of the electron beam. And then the register values are incremented accordingly to account for each pixel. So as the electron beam is going through the scan line, basically the X register will start at 0 and the Y register will start at 0 as well. And then the X register will increment as the electron beam is going down that scan line. Once it reaches the end of that scan line, the Y register will be incremented to 1 to go down to the next scan line, and the X register will be set back at 0 to start the beginning of that scan line, and it would start incrementing to go through that scan line, and this process will keep repeating until the electron beam goes through every single scan line. So to speed up pixel processing, the video controller can actually retrieve multiple pixel values from the frame buffer on each pass. Instead of just grabbing like one pixel value, it could retrieve multiple pixel value. It will store the multiple pixel intensity in a register, in a separate register, which is actually this one, the pixel register, and then use the pixel intensity as stored to control the intensity of the electron beam for a group of adjacent pixels. So instead of affecting just one pixel, it will use what is stored to basically to print out an adjacent group of pixels. Alright, so now that we also have talked about the video controller, before I mentioned that the display processor is also another special purpose processor that a raster scan system could have. And this image over here is a example of a structure of what a raster scan system will look like with a display processor. The display processor is also called graphic controller or display coprocessor. And the thing that's great about the display processor is that it helps free the CPU from as the textbook would it, graphic chores. So anything that the CPU has to do that relates to graphic, the display processor could do it. So it allows the CPU to do other stuff instead. And usually when you have a display processor, there will be a separate display processor memory that is provided with it. And this is the memory that display processor actually uses, so it doesn't actually use the system memory. The major task of the display processor is scan conversion. And the idea of scan conversion is that it's the process of digitizing a picture definition in an application into a set of pixel value that will be stored in the frame buffer. So with the display processor, it actually helps generate different line style, display color area. It helps apply transformation to object. And it's also usually designed to be interfaced with interactive input devices such as mouse or keyboard. Alright, so one important thing with scan conversion is that it actually allows graphic command for straight line and other geometric object to be scan converted into a set of discrete points that correspond to screen pixel position. And these characters can be defined with rectangular pixel grid or with outline shape. So this image up here would be an example of a rectangular pixel grid. And they are actually called like character grid. So it's basically just a rectangular grid pattern that is superimposed into the frame buffer at a specified coordinate position. And then this image down here is actually an example of an outline shape, also called character outline. So basically the shape are scan converted into the frame buffer at a specified coordinate position. So the shape is scan converted, not a rectangular grid pattern. That's basically the difference. And now let's talk a little bit about run length encoding and cell encoding. These are usually used to store value. In these two methods are different ways to store value into the frame buffer. So with run length encoding, each scan line is stored as a set of number pair. The first number is usually the color value, and then the second number will be the number of adjacent pixel on that scan line that is to be displayed in that specific color. With cell encoding, the raster is encoded as a set of rectangular areas. And cell encoding is usually used when pixel colors change linearly. Alright, so now let's talk a little bit about GPU. I'm pretty sure most of us already know what GPU is. Every single computer, laptop, a lot of embedded systems have GPU. They are very powerful. So GPU basically is a graphic processing unit. It's a processor that specializes in handling intensive graphic handling tasks. And what a GPU does is that it lessens the work of the CPU, and it also produces better and faster videos and graphic. GPU is especially high-end, more powerful GPU. They are usually used for high-quality gaming, video editing, 3D modeling, animation, and producing lifelike digital graphics. So the better GPU you have, the better graphics you could get. Alright, and now let's talk a little bit about graphic workstation. So graphic workstation can range from small general purpose computer system to multi-monitor facility. And small general purpose computer could be as simple as just your laptop. To multi-monitor facility could be to like a animation studio with all their computers and PCs. So with personal computer, the screen resolution can vary from 640 by 480 to 1280 by 1024, and the diagonal screen length can range from 12-inch to over 21-inch. So with personal computer, the screen resolution tends to be less, and the length also tends to be smaller. With a desktop workstation that's designed for graphic application, the screen resolution can vary from 1280 by 1024 to 16 by 1200, and the diagonal screen length can be 18 inches or even more. So with these desktop workstations that are more complex and are supposed to be able to handle more powerful graphic application, the screen resolution tends to be a lot better, and the length of the screen tends to also be bigger. So with high definition graphic system, the screen resolution goes up to an extremely crazy high number. It could be up to 2560 by 2048, and these high definition graphic systems are usually used in medical imaging, air traffic control, simulation, and CAD. There are also multi-panel display systems. These are usually used in applications that require wall-size viewing area. It usually shows a large view of a single image or several different images, and multi-panel display systems are usually used to present graphic at like meetings, conference, conventions, those kind of big events that need big graphic display. There are also curved screen systems, and this is usually used for large graphic display. And now graphical input. So we talked about graphic workstation already, and graphic workstation use various devices for data input. So most systems usually have a keyboard and one or more devices designed for interactive input. And just an example of some of these input devices are like mouse, keyboard, trackpad, data glove, image scanner, voice system. All of these are used for graphical input and to be able to get data into these graphic workstation. And Neil will actually be going more in depth about these input devices.
As Jessica mentioned earlier, we need to have input devices to be able to enter information into our graphics workstations. Primarily, we have a keyboard and other input devices. With a keyboard, we can enter text, issue commands, and select options in menu items in programs. Primarily, we input non-graphic data. Function keys are present for frequently accessed features. Additionally, we can have keyboards that contain trackballs, as you may have seen in laptops, as well as joysticks and numeric keypads. In addition to the keyboard, we see a mouse. This is a small handheld unit that's placed on a flat surface that controls the cursor. The mouse has one or more buttons on it. Wheels, rollers, or optical sensors will detect the amount and direction of movement from the user. Now we have graphics tablets, which are also called data tablets. They are a type of digitizer that inputs 2D coordinates on a flat surface through the use of a stylus. They can be sized anywhere from 12-inch by 12-inch up to very large 44-inch by 60-inch displays. They are highly accurate. On desktop versions, you will get about 1/5 of a millimeter in accuracy. In commercial models, you'll see 0.05 millimeters of accuracy or even less. They work by having electrical signals within wires that are placed in a grid fashion. The specific electrical signals will determine the position. There are other types called sonic tablets that use sound waves. The sound from the stylus hitting the surface is timed, and that time is used to create a position. Additionally, we have Polhemus devices. They use alternating current electromagnets. We take these devices as sensors and fix them to objects that we want to track. They're very useful because they provide 6 degrees of freedom. We can track XYZ coordinates as well as the tilting of an object, which can be seen as yaw, pitch, and roll. As we see pictured to the right, there is a data glove. This is used to let users grasp virtual objects. Sensors detect the hand and finger motions. Electromagnetic coupling between antennas will indicate a 3D position. This allows us to manipulate 2D objects on the screen, or if we're using a headset, allows us to manipulate 3D objects in real time. Next, we have 2D and 3D digitizing. In its basic form, a digitizer scans drawings or images for a coordinate system. We have line segments that connect points that will form the edges and curves of an object. As we mentioned with the graphics tablet, this is an example of a 2D digitizer. A 3D digitizer uses sonic or electromagnetic transmissions to record positions. Like the data glove, there is a transmitter and a receiver that computes the location of the stylus. There are different types of scanners. There are small handheld models. There are drum scanners as pictured to the right, as well as flatbed scanners, which you may have used in classes. Scanners pass an optical mechanism over a physical image, and these color gradations are stored in an array. From this array, we can apply transformations, which include rotating, scaling, cropping, and even optical character recognition in the case of text-based data. Now we'll move on to touch panels. These panels allow users to select objects on a screen by simply touching it. There are 3 main types of touch panels. The first is an optical touch panel. There are lines of infrared LEDs along a vertical and a horizontal edge, and corresponding light detectors on the opposite vertical and horizontal edges. These detectors will determine which beams are interrupted, which allow us to determine the coordinate system. The second type is electrical. There are 2 plates, one conductive and one resistive. A touch force causes these 2 plates to contact, which causes a voltage drop, which corresponds to a coordinate. Lastly, we have acoustic touch panels. There are horizontal and vertical high-frequency sound waves in the glass plate. As the user touches the screen, these waves will reflect from the finger to emitters. Then we can calculate the screen position based on the time between transmission and reflection of the wave. As we can see to the right, we have an example of an electrical touch sensor. Next, we have a light pen. These are used for selecting screen positions by detecting CRT light. This pen generates electrical pulse, which causes the coordinate to be recorded. These days, light pens have fallen out of favor, mostly because they obstruct the view of the screen, and they aren't as useful these days. But to the right, we can see an example usage of a light pen. Additionally, they don't work as well when having a black color, because the light pen requires some sort of light to generate that electrical pulse. Next, we have voice systems. These are used as input devices for voice commands. They match input against a predefined dictionary. Traditionally, we have this dictionary set up by repeating the command, and then when the user speaks, the system will find a frequency pattern match. It's helpful in allowing the operator to stay focused on one device. Now we'll move on to hard copy devices. When dealing with images, we oftentimes need to display these images to physical media. With a dot matrix, there is an array of wire pins that protrude or retract based on the desired print and how dark we want a region to be. With a laser printer, the laser creates an image on a rotating drum, and then the toner on the drum transfers to the paper. In an inkjet printer, the printer squirts ink in horizontal rows across paper onto the drum. With electrostatic printers, there's rows of negative charges on the paper that are exposed to positively charged toner. With electrothermal printer, heat is applied to a dot matrix printhead on heat-sensitive paper. To the right, we can see an example of dot matrix printing. Now, we'll move to 3D printers. We use a digital file to create 3D objects in an additive process, in other words, layer by layer. This is the opposite of subtractive manufacturing. This allows us to produce complex shapes with minimal material. In other words, we don't have any casting or dyes required. The most popular type of 3D printing is fused deposition modeling. However, we can see 6 other various types of printers that are also available. To the right, we see the Flash Forge printer, which is commonly available in the DFX lab at USF. Next, we'll move to graphic software. There are 2 main types. Special purpose packages are for non-programmers who want to generate media without coding graphics procedures. To the right, we can see an example of such package. The CAD system is a special purpose package. The second are general programming packages. This is a library of graphics functions that are used by a programming language like C++, Java, Fortran. When we have graphics software, we need a coordinate system to construct and display the scene. Modeling coordinates, which are also called local coordinates or master coordinates, are reference frames for individual objects. For example, a tree, a bicycle, or a piece of furniture. World coordinates describe a scene's reference frame. Viewing coordinates are then used to convert the world coordinates into the perspective of the camera. Then we normalize the coordinates and store 2D values between a range of -1 and 1, or 0 and 1, depending on the system. Lastly, we have device coordinates, which are also called screen coordinates, in the case of video, which are output from the scanned converted picture. To the right, we can see the entire diagram of how we go from the graphic software to the displayed device. Graphics functions enable creation and manipulation of pictures. Control functions are housekeeping tasks. You can think of clearing the display to a selected color, for example. I/O functions control data flow from interactive devices like mice and joysticks. Modeling functions provide individual objects with local coordinates. View transformations will select the view of the scene, the type of projection, and location a view is displayed on monitor. Output functions are building blocks for pictures, for example, text and geometric entities. Attributes indicate how primitives should be displayed, for example, color specifications, line styles, text styles, and filling patterns. Here we can see to the right is an example of object rendering, whereby the first image shows the fully constructed 3D models. To the right, we greatly simplify the view just to what is needed for the user. As a sample program, we have Mesa 3D, which is an open source application that implements OpenGL. And here are our references.